All right, folks, how's it going? How's that lockdown? Right, so realised I got the title wrong. This is actually the second, as well, you know, the second of my catch-up streams, not the first. It should have said part 2, but we're still talking about binary. So what we're going to have a look at tonight is going to be converting binary to hexadecimal and converting hexadecimal back to binary. We will also look at converting denary to hexadecimal and converting hexadecimal back to denary. And maybe if there's time, we'll have a look at how binary is used to store text, graphics, and sound. But I suspect that might have to wait. Okay, so if anyone has any questions, now's the time. But fire them off in the chat or in the Discord. I've got both open at the moment. And if you're tuning in on the rerun, you can pretend to type in the chat, and it'll be just like if you're watching a popular person's stream, because no one is able to actually read and process any stuff that goes into their chats. Right. So here we go. Binary to hexadecimal. Just a quick recap. What is the quick way? There is a quick way of dividing and multiplying binary, which we looked at the end of the last thing. Can someone suggest to me a quick way that we can multiply or divide in binary, and maybe suggest what the answers to these questions 10110000 divided by 8 and 00110101 multiplied by 4. Yes, binary shifts from Tommy and Ollie there. Binary shifts. So if I shift left, does that multiply or divide? And if I shift right, does that multiply or divide? Which direction does which operation? Left. Ooh, here we go. We've got conflicting answers here. Ollie on Discord says left divide and right multiply. Tommy in the YouTube chat says left multiply. Ollie has now corrected himself. Yes, good. Shifting things to the left will multiply stuff. Shifting things to the right will divide stuff. Trying to think if there's an easy way of remembering that. There's an L in multiplied, and left begins with an L, and also the I in right is pronounced like I, and the I in divided is no, because that's the same. I don't know. Just remember it, all right? Left to multiply, right to divide. Actually, the easy way of remembering it is the numbers get progressively bigger the more you move to the left. The numbers get progressively smaller the more you move to the right. Okay, so if I'm going to divide this number by 8, if I'm going to divide this number by 8, obviously we've already established I'm going to be shifting it to the right. How many spaces do I need to shift it to the right? How many spaces am I going to shift? Shift it 3 times to the right is correct. Because remember, it's powers of 2. It's not multiples of 2. Shift it to the right once, that's divided by 2. Shift it to the right twice, that's divided by 4. Shift it to the right 3 times, divided by 8. Shift it to the right 4 times, divided by 16, and so on and so forth. Okay, so 1 0 1 1 0 0 0 0 divided by 8 is going to be 0 0 0 1 0 1 1 0. Okay, and if I'm multiplying this number 0 0 1 1 0 1 0 1, multiplying that by 4, we're going to shift it to the left. How many spaces are we shifting it? Ollie's answer there is just having a look at this. Oh, he's answering a different question. 2 shifts, yes. 2 spaces. Okay, so the shifted value here becomes 1 1 0 1 0 1 0 0. Basically what we're doing is we're taking those zeros off and ended up sticking 2 more zeros on the end there. Excellent. Do you want to do that addition there? 1 1 0 0 1 0 1 1 plus 1 0 1 1 0 1 1 0. If I just fire up GIMP again, you know you love this amazing makeshift whiteboard of mine. File and new. Okay, right. Let me open the thing. Where did I put the GIMP? No. There we go. Okay. Right. So here's my amazing whiteboard. What is the thing? So I just need to adjust the size of my brush here. 1 1 0 0 1 0 1 1 plus 1 0 1 1 0 1 1 0. We're adding those together. If we go through this, let's double check. So we have here 1 plus 0 is 1. 1 plus 1 is 0 and carry 1. 0 plus 1 plus this carried 1 is 0 and carry 1. 1 plus 1 here is 0 and carry 1. 1 plus 1 here is 0 and carry 1. 1 plus 1 here is 0 and carry 1. And 1 plus 1 here is 0 and carry 1. And then finally, 1 plus 1 plus 1 is 1 and carry 1. We have no space here. We can't put that 1 there. Okay. So if we were, the frame rate on this whiteboard, if we were writing that in an exam, obviously that would be our final answer. If I just change my color here, this here is our final answer, all of that, right? You should also specify that it is an overflow. I apologize for the terrible mouse handwriting here. Right, it's an overflow. The way that marks are awarded for questions like this are, I'm marking in red pen here, not green pen, because if you get, if you become insecure when you see red pens, then come on, man, you know, sort it out. You get a mark for getting the final answer right. You get a mark for showing the carry bits in the right place. You get a mark for stating overflow. That's 3 marks. Okay? Are we agreed? Let me hide my whiteboard. Right. Get rid of that. Cool. And we all know what an overflow error is. I'm so mentally numbed to 0.1 frames a year this level of smooth. Yeah, I mean, obviously, if it was up to me, I'd be doing all my online lessons via YouTube, or at least something with a competent streaming method, not via Microsoft Teams. But again, not up to me, because what would I know about computer technology? I'm only a head of computer science. Anyway, moving on. I guess you get a good frame rate on my little wiggly laser thing here as well. I think I'm streaming at 60 frames a second. 144p, 10 frames per second. Is that legit, or is that just you making that up? I don't know. Anyway, an overflow error. Someone tell me, what is an overflow error? Can you explain it briefly, what an overflow error is? There's essentially two different marks that you can get for this question. What is an overflow error? I thought I was about to faint then, but I didn't. Still alive. It shows that I have no trust in Microsoft, Tommy. That's what it shows. Overflow error is when we run out of bits to store the data in. And yes, and why are they bad? So remember, you have a set number of bits assigned, and if the total number of bits that we need to store is greater than the amount that we have allocated for storage, it causes an overflow. Why is it bad? No one knows. Two words. I appreciate that there's a slight delay here. It can cause in-game problems. Yeah, okay, so the example that I gave you was the old Sword of Vermilion, where, yeah, you can end up with mad stats because it sort of wraps around. On the other hand as well, if you ended up, if your maximum number of bits for storing your strength stat, for instance, was 8 bits, and you ended up with, let's say you had a base strength stat of 250, and you equipped the ultimate wooden sword of plus 10 strength or something, that would push you up beyond 255 and potentially would wrap it back round, so you'd end up with a strength of 5, and that ain't going to do any damage. But also, basically, I mean, obviously that's a specific example, but in terms of the issues that it can cause, it's data inaccuracy. Those are the two words to remember. Okay, overflow errors can lead to data inaccuracy. It can cause programs to crash. Obviously, if you're using numbers which are unexpected because you have insufficient bits to store the data, it could potentially lead to those data inconsistencies that can cause it to crash. Okay. Couldn't it be good? What, an overflow? Yeah, there's some applications where overflows are useful. And the benefits of overflows can be exploited. Like Pac-Man, for instance. You've ever played Pac-Man? When the Pac-Man goes off the right-hand side of the screen, he appears on the left-hand side of the screen. There's no funky, special programming going on there. It's a case of it's reached the edge of the screen and it's wrapped back round to the other side. In hacking, right? So we got to lay this on the line here. Yes, you can use overflows to exploit issues and gain access to computer systems. So in a sense, it's good in that it allows you to gain access to these systems. But remember, if you're gaining access to those systems without authorization, then you are breaking the law, and therefore it is a bad thing. So it's good in the sense that you can exploit overflows, things like buffer overflows and stuff like that can be exploited. But yeah, you're absolutely right. Let's say, rather than using the terms good and bad, we can say that overflows are generally not beneficial, but they can be exploited in order to benefit certain tasks. Okay, the exam board wants you to know that they're generally bad things. Okay, it's going to turn my desk lamp on. There you go. Now, did that help? Probably not. pop shield on my microphone is acting as a lampshade. Right, so let's move on. We'll look at hexadecimal. You should know what hexadecimal is, what it looks like. Here's a question for you. Give me some examples. Just type in some example hexadecimal values in the chat. I'm interested here. This is an experiment of sort. Those are all good examples. Excellent. I'm glad you put those ones in as well, Ollie. Anyone else want to give some examples of hexadecimal values? Yeah. F's in chat. So usually, hang on, trying to find out. Oh, right, okay. Worry about the Microsoft Teams maximum specs later on. I imagine, though, if you just look at the standard internet video situation in 1995, that'll probably tell you what it is. So usually when I say give me an example of a hexadecimal number, people start doing things like, I don't know, 3F6E or something. I'm going to enter this, and I don't know whether my stream will have caught up by the time I type that in, right? The temptation is always to put letters in there. Now, obviously, not all hexadecimal values have letters in. 2, 3, like that, for example, is still a hexadecimal value. We need to know whether we are looking at denary or hexadecimal when we look at a number. So although this doesn't come up in the OCR spec, generally speaking, a number is hexadecimal when it's preceded with OX. Like in the chat, for example, right now, OX34 is an example of a hexadecimal number. Okay, in the exam, OCR exam, or any GCSE level computer science exam, they will say to you, this is a hexadecimal number, so that you know. Okay, so we'll have a closer look at how to convert between those different things. Quick question though: if denary is base 10 and binary is base 2, what is the number base of hexadecimal? Spot on, Ollie, and spot on, Obmouse TFM. It is 16. Okay, so base 16. That's where the hexades. That's obviously Greek prefix is there. Each column goes all the way up to 15 before it resets. Okay, in the same way that with denary, which is base 10, we go from 0 to 9 in each column. In binary, which is base 2, we go from 0 to 1. You always go up to 1 less than the base value here. The problem here, obviously, is that we can't go all the way up to 15 using a single digit unless we use some other digits, rather than, because obviously the Arabic numerals that we use for our number system only go up to 9. We need to use other ones. So we use A, B, C, D, E, and F. Right? If we're going to count up in hexadecimal, again, as always, start from 0. 01, 02, 03, 04. When you're reading out hexadecimal numbers, you pronounce every digit, right? 05, 06, 07, 08, 09. And now, ordinarily, if this was denary, what would happen is the 9 would get reset to 0, and we'd end up carrying over the 1 into this column. But because it's hexadecimal, we keep on going. 0A, 0B, 0C, 0D, 0E, and 0F. 0F is equal to 15, right? And exactly the same principle is involved here as any numbering system. We have reached the maximum value that we can represent in a single digit. So what happens is, if we add another 1 onto here, this digit resets to 0, and we end up adding a 1 onto this next column along instead. So 0f plus 1 equals 10. Okay, so 10 in hexadecimal is equal to 16. And then we keep on going. 10, 11, 12, 13. Remember, this is not 13. This is hexadecimal 13. 14, 15, 16, 17, 18, 19. And we're in the same position here. No, we're not, because this is hexadecimal. We're about to transition from the numbers to the letters. So the next value is 1A, 1B, 1C, 1D, 1E, 1F. And then finally, we can't go above F. So this column is going to reset. We add 1 onto this column. So we end up with 20. What value in denary does the hexadecimal value 20 represent? Not 36. Not 36. You're in the right ballpark, but it's not 36. Think about it. 32. Yeah, 32. Because this column represents how many 16s there are. Remember, with our numerical columns, we start off from 1 and we multiply by the base each time. Right? We start off with 1. 1 times 16 is 16. And then 16 times 16 is 256. 256 times 16 is 4096, and so on and so forth. Okay? Now, at GCSE, you only have to deal with 2 columns. Okay? The more complicated maths we do, the more simple maths gets driven from our mind. Can we get a stream chat so I can mute it? I mean, can you not just disable your notifications? No. Okay. Unlucky. So moving on. Converting binary to hexadecimal is super simple. Sorry, I'm trying to keep up with the Discord chat here. I might set up a stream chat, but not right now. Okay. So converting from binary to hexadecimal is super simple. We are going to convert this value 1001 1001. Okay. The first thing that you do is you break your binary number up into nibbles. Remember, a nibble is 4 bits. So if we're dealing with an 8-bit number, it's comprised of 2 bits. That's an easy split, right? If we're dealing with a 6-bit number, you've got to be a little bit careful. I'm just going to fire up my GIMP again here. Right, let me just delete this stuff here. So let's say, for instance, we have a 6-bit number that we're converting. I don't know, 011011. Okay. To split this into nibbles, you do not take that as your starting nibble. No, wrong. Don't do that. Okay. What we need to do is actually oh my god. Oh no, I've ruined everything. I've ruined everything. There. Right. What we need to do is add on a couple of zeros to the start. You need to make it up to a multiple of 4 bits, right? So we end up with this. This is now 2 nibbles, okay? So in essence, what you're doing is you're starting from the back, counting along 4, and then you're padding the front with zeros. Okay, so in the GCSE, they're not going to throw a curveball and give you 6 bits. I'm just saying that because you need to know more about this stuff than just what's in the GCSE if you want to be more than the sum of your parts. Okay, so anyway, getting back to what we've got here, you start off by breaking up this number into nibbles, right? Can any of you remember the connection between nibbles and digits of hexadecimal? Does anyone know what the connection is between each nibble and each digit of hexadecimal and why that connection exists? Does anyone know this? A nibble can represent all the values of one digit of hexadecimal. Yes. Yes. All right. The maximum value that we can represent with a nibble is 15, i.e. there are 16 different values that you can represent, including 0. Right? The maximum value that we can represent with a single digit of hexadecimal is 15, i.e. there are 16 different values, including 0. So yes, that is absolutely correct. W raised to the power of 4, yes. Okay, so that's what it says on this slide. I've literally just explained that. All you've got to do is convert those individual nibbles to denary, and if you have a number which is greater than 9, replace that with the corresponding letter. Okay, so if we're going to do it with this, we'll do it with this number here. Let's gimp it up again. Delete that. Oh God, what have I done? What have I done? There we go. So what numbers did I do? You guys missed that. You missed my abject failure there. I'll take it to my grave with me. 1 1 0 0 0 0 1 1. Okay, this is the number that we are converting. Now, a top tip which I always give to my students, and they always seem to ignore for some reason, is whenever you're doing hexadecimal stuff, it always helps to do something like this just at the side of your paper. A equals 10, B equals 11, C equals 12, D equals 13, E equals 14, F equals respect 15. Okay. Oh, I realised that's actually gone off the screen there. There we go. So having that at the side will lighten your cognitive load. It means that you don't have to be worrying about what the different things are. You've got that table. You've created that table. You can use it to look up. Okay. So first thing that we're going to do is split this into nibbles. So we end up with 1 1 0 0 as our first nibble here, and 0 0 1 1 as our second nibble there. Convert both of these to denary. 1 1 0 0. If you remember the magic numbers here, 8 4 2 1. 8 plus 4 is 12, and over this side 8 4 2 1. Well, 2 plus 1 is 3. Okay, so we have 12 and 3. Looking on my little chart that I handily made here, I can see that 12 is C. Okay, and then all we do is join these together, so we end up with C3, and that is our final answer. Okay, super duper simple. I would say that converting hexadecimal to binary or binary to hexadecimal, they are the two easiest conversions that you'll have to do. Okay, any questions on that bit? Any questions on that bit? What time is it? 4:21. Okay. How much binary things would the exam board give? Who knows? They will almost certainly have at least 2 binary questions, probably some binary addition and some conversions. they will probably have a long-winded question about how data is represented and stuff like that. But you never know. You never know, right? There is no set formula for an exam, okay? But you need to know all of these conversions, okay? So now that we've done that, let's go back from hex to binary, and it's just the reverse, okay? As before, you know, when we were converting from binary to hexadecimal, each nibble represented a single digit. When we're converting from hex back to binary, each digit represents a single nibble, okay? So the process is exactly the same. Let's do it with this one, F7. Okay, I will just clear some of this here. I'm going to keep my little hexadecimal table there. Right, so we're doing F7, right? There it is, F7. Now, first of all, we split up the individual digits. We're going to treat them separately. We have F here. F, I can see, is equal to 15. And 7 is just 7. So now I can convert this to binary. 15 in 4-bit binary is 1, 1, 1, 1. Okay, 8 plus 4 plus 2 plus 1. I specifically haven't done any working out there. You should ideally know the 16 numbers from 0 to 15 in 4-bit binary. It's there's only 16 of them, right? It's not hard to remember. Okay, and likewise 7 is going to be 0, 1, 1, 1. Okay, once I've worked out both of those, I can just, like before, join them together to give 1, 1, 1, 1, 0, 1, 1, 1. And that's our final answer. That really is all there is to it. Super duper easy, right? So important things to remember there: split your digits, convert to denary if it's a letter, then convert to individual nibbles and join them together again. When you're converting from binary to hex, you start off with by splitting it into nibbles, convert them to denary, replace with letters where necessary, and join them together. Make sense? Cool. I assume it makes sense, seeing as no one's saying anything. Okay. Oh, look, there's the answer. Right. Now, this is the... could you say F7 is 8 away from the max, so you just take 8 from the max binary? I mean, sure. But at the same time, it's better to have a consistent method for this, because not all numbers are going to be that nice. You know, as an example, if I had something like... I don't know, 6, 3. Okay, got to split these bits up. Okay, we end up with 6, which is 0, 1, 1, 0, and we end up with 3, which is 0, 0, 1, 1, and then join both of them together. That's supposed to be an arrow, by the way. 0, 1, 1, 0, 0, 0, 1, 1. Okay, obviously that one's less obvious, right? So it's good to have a consistent method. Okay. Right, so hexadecimal to denary. This is... do you say you can't see the GIMP? Oh no. Can you see it now? I thought it was on the screen. Yes, good. So I'll pretend to do that again. 6, 3, split them up. We've got a 6 here, we've got a 3 there. The 6 is 0, 1, 1, 0. The 3 is 0, 0, 1, 1. Join them together, 0, 1, 1, 0, 0, 0, 1, 1. Okay, so again, like I said, helps to have a consistent method for these conversions. Sorry about that. I thought GIMP was on there. Right. Next up, hexadecimal to denary. This is very similar to binary to denary, but the numbers are a little bit more like tricky. Okay, because we're not just dealing with zeros and ones here. We have a range of different numbers that could go in each column. Okay, but the same principle applies. The same principle applies. Okay, remember in binary, you'd write out the table 128, 64, 32, 16, 8, 4, 2, 1, and any columns with a 1 underneath, you'd add that on. Well, we're doing exactly the same thing here, except for hexadecimal, you only have 2 columns. It's base 16, so you're going to have 1, you're going to have 16. Okay? The critical thing to remember is this. You multiply the first column by 16. Right? And then you add the second column on. Technically, what you're doing is you're multiplying this second column by 1 and then adding it together. Right, but that's no different to how you would do it for a binary number. Right, I'm going to turn my GIMP back on here. What was the number that I had there? F3. Right, okay. So let me just delete this stuff here. Go away. Okay, so I can't remember what it was now. Was it F7? F3. So we have F3, right? Now, before I do this, just a quick example of converting a binary number to denary. If I had something like 1011, I'll just do a 4-bit number here. I have my magic numbers above the columns here, 8, 4, 2, 1, right? To convert this, we have 8 because there's a 1 underneath that. We don't add 4, but we do add 2 because there's a 1 underneath that, and there's a 1 underneath the 1, so we're going to add all of those together. 8 plus 2 plus 1 is 11. 1011 is equal to 11, right? What we're actually doing here is we're doing whatever number is on the bottom multiplied by whatever number is on the top and add them all together. 1 times 8 is 8. Plus 0 times 4. Well, 0 times 4 is 0. So what we're effectively doing is 8 plus 0 plus 2 plus 1, right? And then we've got 1 times 2 and we're adding that on. We've got 1 times 1 and we're adding that on, right? The basic principle is exactly the same here, right? Let me just erase that stuff. So we have our F3. If we were to write that out in little columns, right, we have F here, we have 3 here. The magic number here is 16. The magic number here is 1, right? That's no different to the way that we did our binary conversion there. You've just got to remember it's 16. And we're doing this multiplied by this plus this multiplied by this. Anything that's on the bottom, you multiply by the stuff which is on the top. Okay, so what we're doing is F times 16. Well, F is equal to 15. So that is equal to 15. That looks like a 16, sorry. 15 times 16. Okay, 15 times 16 is 240. That's a 0. 240. Okay, we're not done yet because all that does, that just gives us the this lot here. That just gives us this value here, right? We still need to add this value here, right? So what we then need to do is effectively 3 times 1, which is 3, and we're going to add those together. Right? You don't have to do 3 times 1, obviously, but I'm just going over it to show you the principle behind it here. Right? So that there is equivalent to this column here. So you add them together. So we have 240 plus 3, which is 243. Okay? So things to remember. First digit times 16 plus second digit. That is the method. It's always that. Remember, the first digit is worth more than the second digit. You've just got to remember, it's base 16. Yeah? Any questions on that bit there? Any questions on that bit? Are we going to get any hex numbers that are longer than 2 digits? Not at GCSE level, no. It's always going to be 2 digits. It's always going to be bytes. Okay? Done that. This presentation, by the way, is shared up on the Google Classroom, so you can see my working out here. But there, I've done it. I've already done it for you on the GIMPs. Okay. Won't do this practice yet because of the time. Right, denary to hexadecimal is the most challenging of all of them. Okay, this is the one that people hate, mostly because it involves dividing by 16. But there are some easier ways of doing it. Okay, so I've got a couple of methods that I can show you. Because the thing to bear in mind is that you might think, what, 77 divided by 16 is easy, just use a calculator, man. Remember, you are not able to use a calculator in the exam. That was the word I was looking for. Okay, no calculators allowed. Okay, so let's have a look at how this works. 77 is what we're going to convert. Okay, now in effect it's the reverse of this. Yeah, you're dividing by 16 rather than multiplying by 16. That's green. Nice one. Nice one. Okay, so let's go back to my thing here. We've got 77 is the number that we are going to convert here. Right. Now, if you think about the way that binary works, if I have a denary number and I'm trying to convert back to binary, we start off from the left-hand side, and what we do is we check to see whether that 128 is greater than or less than, and we write the ones in and stuff like that. What we're actually doing there is dividing by 2 each time and producing the remainder. Okay, but rather than me going into the ins and outs of the binary right now, let's just focus on the hexadecimal. Right, so you take your number, you divide by 16. Okay, that gives you your first digit. Yeah, and when I say divide by 16, I'm not interested in any decimal points or anything like that. It's the quotient that we're looking for. In Python, you use your integer division, 2 forward slashes. Okay, that's your first digit. To get the second digit, it's the remainder. Right, the remainder of 77 divided by 16 gives the second digit. Okay, so in Python you would use the mod function to get that. Yeah, so what I'm doing essentially is 77 divided by 16. Now, if you're totally hot on your 16 times table, you will probably know that that's what, 4? Is that 4 times 16? Because 5 times 16 is 80, right? Am I right there? 77 divided by 16, I think, is 4. What's 4 times 16? It's 64, right? Yeah. Which means our first digit here is our first digit is 4. Right? Now, there's two ways of working out the remainder. Probably the most straightforward way is working out what 16 times 4 is and then subtracting that from 77. Okay, so 16 times 4 is 64. Right? If I now do, that's times. If I do 77 minus 64, so 7 minus 4 is 3, this is minus. 7 minus 6 is 1. I can see the remainder is 13, right? So So 13, that's our second digit. Look up 13 and it is D. Okay, that's our second digit. Now, if this seems long-winded, there is a slightly easier way. There's our second digit there. Okay, so this is sort of the traditional way, if you like. Take your number, divide by 16, that gives you the first digit, and the remainder of that division is your second digit. Okay, now there's a lot of people that look at that and they think, doing that without a calculator, are you mad? Well, there is a slightly less convoluted way of doing it, or maybe it's more convoluted, I don't know. I will show you, and you can use whichever way works best for you. Okay, because if I divide by divide by 2 4 times, that is the same as dividing by 16, right? So here's a little trick that you can use. Let's just delete all that lot. Oh no. There we go. So instead of dividing by 16 right off the bat, yeah, I would do 77. Okay, and what I'm going to do is this column here holds the remainder, right? And over here we are 1, 2, 3, 4, yeah. So divide by 2, divide by 2. Obviously you don't have to write all of this out. I'm just doing this for demonstration purposes here. Okay. Now remember, working out the remainder when you're dividing by 2 is easy. If the number that you're starting off with is even, the remainder will be 0. If the number that you're starting off with is odd, the remainder will be 1. So I can work out what that remainder is before I even do any like division here. 77 divided by 2, that's an odd number, so the remainder is going to be 1 there. I know that straight off the bat. Okay. So what I now need to do effectively is 76 divided by 2, which I believe is 38. 7 divided by 2 is 3, remainder 1, and 16 divided by 2, yes, that is 38. Okay, now we're not done yet. We're going to keep on trucking. We are now dividing this number by 2. 38 divided by 2, it's an even number, so I know the remainder's going to be 0. Okay, so 38 divided by 2 is 19. Yeah. 19 is odd, so this is going to be remainder 1. 19 divided by 2 is 9. 9 remainder 1. That's an odd number, so I know the remainder is going to be 1. And then 9 divided by 2 is 4. Okay, with me so far? So what we've done here, 77 divided by 2 is 38. 38 divided by 2 is the same as 77 divided by 4. 19 divided by 2 is the same as 38 divided by 4, which is the same as 77 divided by 8. Right? This kind of ties in with that stuff that we did with binary shifts. Yeah? And so 9 divided by 2 is the same as 19 divided by 4. It's the same as 38 divided by 8. It's the same as 77 divided by 16. Therefore, this here is our first digit. Okay, our first hexadecimal digit is that 4. Because that's the same as dividing by 16. So what do we now do with this remainder? Well, the whole of this remainder is effectively, let's choose that nice green, is effectively our second digit. But what we need to do is we need to sort of rotate it round this way, okay, to give us 1101. Okay, down here, this is the most significant number, because if you think about it, that makes sense, right? This is the remainder of this number divided by 2. So if we're sort of like multiplying this up the chain, that's actually, it's 1 there, but if I multiply that by 2, it becomes 2. If I multiply that by 2, it becomes 4. If I multiply that by 2, it becomes 8. Right, this one here is 1 there, but if I multiply that by 2, it becomes 2. If I multiply that by 2, it becomes 4. These are our magic numbers, right? So the further down this number is, the more significant the number will be. So all we then need to do is convert this number here. Oh, it's gone off the screen. I'm sorry. How's that? How's that? Right. We convert this number here to denary. Okay. I apologise for the absolute scuffed nature of this stream, but it's still better than PragerU, which is the worst YouTube channel in the universe. So we convert this now to denary. 8 plus 4 plus 1 is 11. We can see that 11... Hang on, I've messed up somewhere. Sorry, no, it's 13, isn't it? 8 plus 4 plus 1 is 13. It's 13, yes. 13 is equivalent to D. And so once again, we have 4D as our answer. Okay. Look, it's been a long day, Tommy, all right? It's still sort of off the screen, isn't it? There we go. Is that... God's sake. Can you see that? Is that all right? I'm sorry. All right. So there's two different ways of converting from denary to hexadecimal. Okay. You can either divide by 16 to get the first digit and then state the remainder as your second digit, or you can divide by 2 4 times, noting the remainder each time, convert this number to denary and then convert it to a letter. Okay? Does that make sense to everyone? I hope it makes sense to everyone. It makes sense to me, but then I know this stuff anyway. There is no law that says you have to use one method over the other. You use whatever method makes the most sense to you. If any teacher ever says to you, this is the way that you have to do something, that's a bad teacher, right? If you can work out a method that works for you and gives the same result without any issues, then that's fine. You know, why should it be any different? Okay, let me just undo that. I've got a little table here again showing the things here. 77 divided by 2 is 38. 38 divided by 2 is 19. 19 divided by 2 is 9. 19 divided by 2 is 4. And here's our 1 0 1 1 there. Okay. All right, and that's that. I don't have time to explain the ins and outs of how data is stored using binary and hexadecimal. We will look at that in the next stream. Okay, so you should now be reasonably confident in converting binary to hexadecimal, hexadecimal to binary, denary to hexadecimal, and hexadecimal to denary. If you need to go back and double check those exercises on the classroom, then by all means do so. If anyone has any questions, now is the time. What about cheating? That works for me. Well, I mean, here's the thing, yeah. What is cheating? You know, I mean, exams. Why do exams exist? They seem an outdated way of testing someone's ability with a subject. Because an exam is just a test of how much stuff you can remember most of the time. And at what point in your life are you going to be in a situation where you desperately need to remember stuff? Your boss is not going to come up to you and say, I need you to do this task, and you're not allowed to look on the internet, and you're not allowed to talk to anyone, and you've got to do it in silence, right? It's a nonsense. A better way of assessing your ability would be to give you some sort of project which would require you to show the application of that knowledge, because the application of the knowledge is so much more important than the knowledge itself, right? So here's a challenge. You've got a week to get it done. You've got full access to all of the information that you'll need. You know, how'd you get that done, right? There you go. When you go to Tesco and forget your shopping list, that's cheating, is it? I don't know about that. You need to remember a lot of stuff in that situation. I mean, but that's not really a test of your knowledge, is it? That's more of a test of your organisational skills. But yeah, well, and also, is shopping a GCSE? Is that a course that you can do? I don't really think so. So yeah, there is that. More useful than English. Look, the English language is a beautiful thing, and it's a bizarre thing. It's not. All I will say is that the British education system tends to do a very good job of squeezing the joy out of most subjects. Okay, so the things that you hate in school, you might not always hate them. I hated history in school, but I spend so much time reading like history books these days. I actually hated computing in school as well, because it was so boring. It was so boring. You know, type this data into a database. Now run a query on the database. No, it's dull, you know. But that's why I try and make my lessons that little bit more interesting. And that's why I throw in stuff which is not on the spec. So you know, there's a lot of stuff that we cover which is not on the spec. It's on the A-level spec, and some of it is beyond A-level as well. But it's my job to teach you about computer science. It's not my job to coach you through an exam. And I fundamentally disagree with anyone that thinks that coaching for an exam is an acceptable practice. If you call yourself a teacher and all you do is teach to the test, then sorry, you're not a teacher. You're a fraud. But anyway, with that rant over, I assume there's no more questions. Otherwise, you guys would have posted those questions already. We've been online for about an hour. So I can see that Ollie is typing, and so is Tommy. Hope these are questions and not nonsense. They've stopped typing. Is that because they were nonsense? Right, I'm gonna end the stream now. I will. Any questions that you have, I'll answer on Discord. All right. Thanks very much for your time, everybody. Hope this has been enlightening. Yeah. Okay. And I will see you. I'll see you in a bit.